Welcome viewers to NPTEL's lectures on integral equations. This is going to be the first lecture on integral equation. Now, integral equation is a very useful tool in mathematics from pure mathematical point of view as well as from applied mathematical point of view, and there are different areas where this type of integral equations are used in a wide sense. Now, first we start with our known formulation, that is ordinary differential equation, from where we can see how integral equation comes into the picture. Now, for this purpose we consider initial value problem which is usually denoted by IVP of ordinary differential equations. This is in general denoted by ODE, and throughout this lecture series I will use this IVP and ODE for initial value problem and ordinary differential equations. So, first of all we consider a general first order differential equations equal to fxy subject to the initial condition y x0, this is equal to y0. For this kind of equations we know how to solve this problem. Now, our intention is to convert this initial value problem to an integral equation. So, in order to solve it we can write dy, this is equal to f xy dx. Now, if we integrate between y equal to y0 to y and x equal to x0 to x, then you can find y0 to y dy, this is equal to integral x0 to x f of s y s ds, from where we find y, this is equal to y0 plus integral x0 to x f of s y s ds. Now, this yx equal to y0 plus integral x0 to x f s y s ds, this is actually our integral equation, because the unknown function y here appeared under the integral sign. Now, if y equal to yx is a solution of this equation, that is the initial value problem, then same function yx will be a solution of this integral equation. Now, if we just look at this equation, so in this case we have to find out yx such that yx satisfies this equation. Next, we consider a particular example to verify whether a solution of the initial value problem is going to satisfy the corresponding integral equation or not. For this purpose we choose the equation dy dx is equal to 2xy subjected to the initial condition y0, this is equal to 1. So, this is our given ODE, and of course, this is an initial value problem, and you can easily verify solution to this problem is given by y equal to e to the power x square. If we recall the last equation what we have constructed, once dy dx equal to f x y subject to y x 0 equal to y 0. So, this is our integral equation. So, corresponding to this given differential equation, our integral equation will be yx, this is equal to 1, that is y0, plus integral 0 to x to s ys ds. Now, here we are intended to verify whether this yx equal to e to the power x square will satisfy this or not. So, for this purpose we start with right hand side. So, this is equal to 1 plus integral 0 to x to s. Now, ys is e to the power s square ds, and if we integrate it, then we find 1 plus e to the power s square integral from limit from 0 to x. So, this is coming out to be e to the power x square, which is equal to left hand side. So, that means the solution of this initial value problem is also a solution to the corresponding integral equation. Now, it was a first order equation. Next we consider a second order ordinary differential equation. Again, this is a second order initial value problem. We consider this equation d2y dx2 plus 2 dy dx plus y equal to x square with given initial condition y0 equal to 1 and y dash 0, this is equal to 0. Now, at a later stage of this lecture series, I will show you directly from here after integration how can we find out the integral equation. Now, as it is a starting point, here we just consider second derivative of y with respect to x. We define it as a new function phi x, such that after integrating this expression twice, that means we are going to evaluate dy dx and y in terms of phi and its integral, such that the entire equation can be converted into an integral equation. So, this equation we can rewrite as d of dy dx, this is equal to phi x dx. Now, here initial condition is given at x equal to 0. So, if we integrate from 0 to x, so then you can find dy dx minus 0. This 0 is coming due to the given condition y dot 0 equal to 0. This is equal to integral 0 to x phi s ds. So, this actually implies dy dx is coming out to be integral 0 to x phi s ds, call it 2. Again, if we integrate this result after transferring dx onto the right and again from the limit 0 to x, then we can find yx minus y0, this is equal to, now here range of integration is going to be x. So, we change this limit to t and we get 0 to x integral 0 to t phi s ds dt, and this y0 is equal to 1. So, this implies yx, this is equal to 1 plus integral 0 to x integral 0 to t phi s ds dt. Now, if we look at the range of the integration, in this direction we can take s, in a vertical direction we can take t. Now, first limit was on ds and s is ranging from 0 to t. So, that means we have a straight line whose equation is s equal to t. So, ds varies from 0 to t, and then this limit t varying from 0 up to the line, that is t equal to x. So, this area is actually our domain over which we are performing our integration. Now, if we interchange the order of the integral, then after interchanging the order of integral, we can find this is going to be 1 plus integral 0 to x minus s phi s ds. So, interchanging the variable of integration, we will be getting this equal to y. So, we have assumed d2y dx2 equal to phi x, then from there we have derived using the given initial condition y dot 0 equal to 0, that dy dx equal to this one, and finally using y0 equal to 1, we have obtained yx equal to this one. Now, if we substitute all these expressions into the given equation, then you will be having 1 plus integral 0 to x minus s phi s ds. This is actually coming out for y, then plus 2 integral 0 to x phi s ds plus phi x, this is equal to x square, and from here we can write that phi x, this is equal to x square minus 1 minus integral 0 to x 2 plus x minus s multiplied with phi s ds. So, in this case you can see phi is our unknown and this phi x comes under integral sign. So, this is an integral equation corresponding to the given second order initial value problem. Now, if yx is a solution to the given second order initial value problem, then second derivative of y, that means y double dot x equal to phi x, will be the solution of this integral equation. Now, so far we have considered two initial value problem, and in both the cases resulting equation comes out to be an integral involving 0 to x within this range. Next we consider a boundary value problem. This boundary value problem is denoted by BVP. Consider the second order differential equation d2y dx2 plus omega square y, this is equal to 0, subject to the given boundary conditions y0 equal to 0 and y alpha, this is equal to 0. So, that means we are considering this problem over the interval 0 alpha, that is x ranging from 0 to alpha. Now, in the previous example, in order to convert this type of second order differential equation to an integral equation, we have chosen d2y dx2 equal to phi x. Now, here without introducing that type of function, directly we can make an attempt to convert this equation to an integral equation. At a later stage of this lecture series, I will describe in which cases we have to consider what type of technique to convert the differential equation into integral equation. But that is not a very serious question, because most of the time we will be considering solution of the integral equation. Now, this equation can be rewritten as d dx of dy dx, this is well known strategy, is equal to minus omega square y x. Now, if we integrate this equation from 0 to x, then you can find dy dx minus this derivative of y evaluated at y equal to 0, that is y dot 0, this is equal to minus omega square integral 0 to x y s ds. Now, in this boundary value problem, the values of y on the left hand and on the right hand are given. We do not have any information for y dot 0, but at a later stage, using this boundary condition, we can find out y dot 0 in terms of y. So, from here we can write dy dx, this is equal to y dot 0 minus omega square integral 0 to x y s ds. If we again integrate the previous expression, then we can find y x minus y 0, this will be equal to y dot 0 multiplied by x minus omega square integral 0 to x integral 0 to t y s ds dt. Now, you can recall that given condition for y 0 was 0. So, from here we can write y x is equal to y dot 0 x minus omega square, and again if we apply the same technique as we have adopted earlier, from here we can find integral 0 to x x minus s y s ds. Still this y dot 0 is appearing here. Now, we can make an attempt to find out this y dot 0. If we substitute x equal to alpha in this result, then we can find 0, this is equal to y alpha. Actually, substituting x equal to alpha, you will be having y alpha here, and y alpha is given to be 0. So, 0 equal to y dot 0 alpha minus omega square integral 0 to alpha alpha minus s y s ds. So, from here we find y dot 0, that is equal to omega square divided by alpha integral 0 to alpha alpha minus s y s ds. So, if we substitute this expression here, then we find y x, this is equal to omega square times x by alpha integral 0 to alpha alpha minus s y s ds, this part coming for y dot 0, then minus omega square integral 0 to x minus s y s ds. Now, we have to proceed further in order to put this integral equation into more compact form. In order to put it into more compact form, we can use this identity x minus s, this is equal to x by alpha times alpha minus s minus s by alpha times alpha minus x. This is an identity, and we are going to replace this x minus s with help of this result. So, if we replace this x minus s by this identity, then we find y s equal to omega square times integral 0 to alpha x by alpha alpha minus s ds minus omega square integral 0 to x by alpha times alpha minus s y s ds plus omega square integral 0 to x s by alpha times alpha minus x y s ds. Here I forgot to write y s, this will be y s ds. Now, here range of integration is 0 to alpha. So, we can divide this range of integration 0 to alpha by introducing a point here, that is 0 to x and x to alpha. So, if we divide this into 0 to x and x to alpha, then 0 to x integral will cancels with this one, and then we are left with this is equal to omega square integral x to alpha x by alpha times alpha minus s y s ds plus omega square integral 0 to x s by alpha times alpha minus x y s ds. So, this is equal to omega square under bracket 0 to x s by alpha times alpha minus x y s ds plus integral x to alpha x by alpha times alpha minus s y s ds, and this can be written into a compact form omega square times integral 0 to alpha k x comma s y s ds, where this k x comma s is defined in this way. This is s by alpha times alpha minus x whenever s less than x, and this is equal to x by alpha times alpha minus s for x less than s. So, that means y x equal to omega square integral 0 to alpha k x comma s y s ds. This is the integral equation corresponding to the given second order boundary value problem. Now, here I give just some exercises that you can try to convert this problem to integral equations. So, the problem is write integral equations for the given initial value problems. Number 1, dy dx minus 2 xy equal to e to the power 2x with given initial condition y0 equal to 1. Problem number 2, d2y dx2 minus sin x dy dx plus e to the power x into y, this is equal to x with initial condition y0 equal to 1 and y dot 0, this is equal to minus 1. Problem number 3, d2y dx2 plus 1 plus x square y, this is equal to cosine x with given initial condition y0 equal to 0, y dot 0, this is equal to 2. And problem number 4, d4 y by dx4 plus 2 d2y dx2 plus y, this is equal to 0 with the given initial conditions y0 equal to y dot 0 equal to y double dot 0, this is equal to 0 and y triple dot 0, this is equal to 1. So, this was all examples based upon the ordinary differential equation, such that ordinary differential equations can be converted into integral equations. Now, I give a physical example regarding the origin of integral equation. This integral equation is actually known as Abel's integral equation, and this problem is related with isochron curve. This isochron curve problem is something like that. You have a curve like this, a particle starts from this point, it is coming down along the curve under gravitational force only, and this wear is a frictionless wear, and suppose this is the point up to which this particle can come down. So, the problem is that this isochron curve is the curve for which the time taken by an object sliding without friction under uniform gravity to its lowest point, this point is the lowest point, is independent of its starting point. So, main problem is we have to find out the shape of the curve such that if we start from either at this position or at this position or at this position, all the particles will arrive at the fixed point at the same time. Now, let us denote capital T is the time taken by a particle coming to the lowest point from a vertical height h. So, this is the h stands for vertical height through which the particle came down along this particular curve. Now, there is no friction. If we look at the geometry and relation with the coordinates, you can see this is the x axis origin, this is y axis, curve is something like this one, and this is the position of the particle at any time t, weight mg acting vertically downwards. So, this height from the lowest point can be measured as the y coordinate of this particular position. Suppose it started from a height h somewhere here, then at this point kinetic energy, this is nothing but half of m v square, and since the particle is coming along a smooth curve, so this is equal to half m ds dt whole square. S is the arc length of this particular curve at this position, and potential energy, this is equal to mg multiplied by the height through it descends, and as it is a smooth curve, there is no friction, therefore, kinetic energy will be equal to potential energy as per the conservation of energy is concerned. So, from there we can write half m ds dt this whole square is equal to mg times h minus y. This m cancels from both sides, and from here we can write dt, this is equal to plus minus ds divided by root over 2g times h minus y. Now, we need one assumption regarding the equation of this curve. Without any loss of generality, we can assume we can find out this arc length in terms of y coordinate of the point, and then using the chain rule we can write ds equal to ds dy times dy. So, if we use this result here, then we will be having dt, this is equal to plus minus ds by dy divided by root over 2g times h minus y dy. Now, if we just go back to the previous picture, then you can see the remaining distances, this actually height decreases with the increase of time. This height y, remaining height, this is a decreasing function with the increase in t, and therefore, we take negative sign to get this result dt equal to minus ds by dy divided by root over 2g into h minus y dy, and then the time required for coming to the lowest point from a height h, that is th, is given by 1 by root over 2g integral 0 to h ds dy divided by root over h minus y dy. This equation is actually called Abel's integral equation. This is called Abel's integral equation. So, the problem is that Ht is given and we are interested to find out ds dy, for which the equation of the curve can be obtained such that a particle starts from any height, it will reach at the lowest point that will be independent of the height from where it has been started. So, this is one physical example behind the formation of integral equation. Now, we are in a position to give the general definition of an integral equation. In general, integral equation is given by this particular format: y x is equal to f x plus lambda times integral a to b k x comma s y s ds, where a less than equal to x comma s less than equal to b. So, the problem is we have to find out y x such that this equation is satisfied, and the unknown function y is under the integral sign, and that is why this equation is called an integral equation. And here f x, this is a given function, k x comma s, this is actually called kernel of the integral equation. This is kernel of the integral equation, and lambda, this is a parameter. Now, in some of the problem, this upper limit b may be a variable x, and in some cases either lower limit or upper limit or both of them will be infinite quantities, and depending upon whether both the limits are finite real numbers or upper limit is a variable x or the limits are infinite, based upon this we can classify this integral equation into different classes. Now, before going to that, I want to attract your attention towards the most important point, that linear integral equations. The integral equation what I have written here, that is actually a linear integral equation, because y appeared in this equation having the first power. In general, we can define the linearity property in this way. Entire equation can be written in the form as a operator L y x, this is equal to f x. If we denote this y x minus lambda times integral a to b k x comma s y s ds as L of y x, then we can easily check for this equation it satisfies the condition L of C 1 y 1 x plus C 2 y 2 x, this is equal to C 1 L of y 1 x plus C 2 L of y 2 x. this is the linearity condition where C1 and C2 are two constants. So, this is actually the standard form of linear integral equation. Of course, you will be curious to know what will be the format of the nonlinear integral equation. I am just giving you some examples, that is y x is equal to integral a to x k x comma s y s whole cube ds. Here the unknown function y appeared as y cube, which is a nonlinear function of y, and hence this is a nonlinear integral equation. Another example y x, this is equal to f x plus 2 integral 0 to 1 k x comma s e to the power y s ds. This is again another example of nonlinear integral equations. These are actually nonlinear integral equations. Now, we come to the classification of different linear integral equation. First, we consider Fredholm. Fredholm linear integral equations. These Fredholm linear integral equations are written as psi x y x equal to f x plus lambda integral a to b k x comma s y s ds, where a less than equal to x comma s less than equal to b. This psi is actually introduced here in order to classify further this integral equation into two types, that is Fredholm linear integral equation of first kind and Fredholm linear integral equation of the second kind. For psi x equal to 0, then we will be having this integral equation of the form f x plus lambda integral a to b k of x comma s y s ds. This is equal to 0. This is actually Fredholm linear integral equation of the first kind. This is important, Fredholm integral equation of the first kind. And if we take psi x equal to 1, then equation is y x equal to f x plus lambda integral a to b k of x comma s y s ds. This is actually Fredholm integral equation of second kind. Next, we consider Volterra linear integral equations. These Volterra linear integral equations, in this case one limit is coming out to be a variable limit. General format is psi x y x is equal to f x plus lambda times integral a to x k x comma s y s ds. So, this x comes out here, appears here instead of earlier b. So, these type of equations are actually known as Volterra linear integral equations. I am not repeating the same thing, and just for your note that if psi x this is equal to 0, then we will be having Volterra linear integral equations of the first kind. And similarly as above, if psi x equal to 1, then we will be having Volterra integral equation of the second kind. So, these two things are related only with the fact that whether y x appearing outside the integral signs also or not. So, based upon this we can classify them into Volterra integral equation of first kind or second kind and Fredholm integral equation of the first kind or second kind. Now, we just look at some particular features. In case of Fredholm linear integral equation, range of integration is finite, and we have to find out this unknown function y x. In case of Volterra integral equation, the range of integration is variable, one upper limit is variable, lower limit is a fixed constant a. In some problem this may be the reversed one, the lower one is a variable x, upper one is some constant b. Next we comes to the homogeneous integral equations. These homogeneous integral equations, these are related with the appearance of f x. If f x is identically equal to 0, then we can find homogeneous integral equations. So, homogeneous integral equation of Fredholm type, we consider just one example, that lambda 0 to 1 x minus s y s ds. This is an Fredholm homogeneous integral equation, and y x is equal to 2 integral 0 to x k x comma s y s ds. This is an example of Volterra integral equation which is homogeneous. Next we consider another classification that is known as singular integral equation. In case of singular integral equation, either lower limit or upper limit or both the lower and upper limits are infinite quantities, or integrand may have one or more singularities within the range of integration. If this happens, then integral equations are known as singular integral equations. We just consider few examples of singular integral equations. Y x, this is equal to cos x plus integral 0 to infinity sine of x minus s y s ds. This is an example of singular integral equation. Another one is yx equal to fx plus lambda integral minus infinity to plus infinity e to the power minus x minus s y s ds. This is another singular integral equation. In the first one, upper limit is infinite. In the second one, lower limit and upper limit, both of them are infinite. And another integral equation yx is equal to integral 0 to x ys ds divided by x minus s to the power alpha, where 0 less than alpha less than 1. So, at s equal to x, this integrand is infinite. So, x equal to s is a singular point of this integrand, and therefore, this is a singular integral equation. Finally, for today we just consider one problem, that is solution of an integral equation. We are not going to solve any integral equation, rather we can verify that a given function satisfies an integral equation. Here we are going to verify that f(x) equal to 1 by pi root over x. This is a solution of the integral equation given by 0 to x y s divided by root over x minus s ds. This is equal to 1. So, in order to verify this, we start from here 0 to x y s by root over x minus s ds. So, substituting for y s equal to 1 by pi root over s, we can find this is equal to 1 by pi integral 0 to x ds divided by root over x s minus s square. This is equal to 1 by pi integral 0 to x ds divided by root over x square by 4 minus s minus x by 2 this whole square. This is equal to 1 by pi sin inverse s minus x by 2 whole divided by x by 2 and limit 0 to x. So, this is equal to 1 by pi. After substituting the limit, we will be having sin inverse 1 minus sin inverse minus 1. Considering principal values of this inverse function, we find this is equal to 1 by pi, pi by 2 minus pi by 2. So, this is equal to 1. So, that means the function f(x) equal to 1 by pi root over x satisfies this integral equation, where y was the unknown and this 1 by pi root over x, this is the solution of this integral equation. So, just in order to sum up, first of all, today we have seen that how ordinary differential equations, they are either initial value problem or boundary value problems, that can be converted into integral equations. Then we have considered a physical problem behind the formation of integral equation, and after that we have classified different types of integral equations. We have considered Fredholm integral equations. These are of two types, that is first kind and second kind. Then Volterra integral equations, and then we have had a look at homogeneous integral equations, and finally we had a look at the singular integral equations. Now, in rest of the lectures, most of the time we will be considering linear integral equations only, and at the end I just give one lecture on the solution of nonlinear integral equations.